Section: Introduction. In this section, we explore how humans can flexibly understand and apply abstract concepts to interpret the world around us. For example, when we think of a maze, we can recognize it regardless of whether it's made from traditional materials like drawn lines or unconventional ones like icing. Our aim is to create systems that can generalize in the same flexible way as humans do. This leads us to a key question: what defines a maze? It's not just about its physical features, like the materials used or the shape of the walls, but rather the underlying rules that govern its structure. A maze can be represented in many forms, whether the walls are made of candy canes or popsicle sticks, yet they all share the same conceptual framework. However, current vision language models, VLMs, often struggle to grasp these abstract concepts, tending to interpret images literally rather than understanding the deeper meaning. For instance, when presented with an image of a maze made from unusual objects, models like GPT-4V and LLaVA may fail to recognize these objects as part of the maze concept. This raises questions about whether these models can truly understand abstract concepts like humans do. To tackle this issue, we propose Deep Schema Grounding, DSG, a framework designed to help models interpret visual abstractions. At the heart of DSG are schemas, which are structured representations of abstract concepts. These schemas help us understand common patterns in how we interpret the visual world. For example, a schema for helping helps us understand interactions in a puppet show, while a schema for tic-tac-toe allows us to play the game even if the grid is made of hula hoops. The schema for maze is what allows us to recognize a maze as a maze. DSG utilizes schemas generated by large pre-trained models to reason about visual abstractions. We represent schemas as programs that break down an abstract concept into more concrete visual elements. Our framework consists of 3 steps. First, we extract schema definitions from a large language model, LLM. Second, we query a vision language model, VLM, to ground concrete symbols in the schema. And finally, we use the resolved schema to provide context for the image, enhancing our ability to reason about it. To evaluate how well models understand visual abstractions, we introduce the Visual Abstractions Dataset, VAD, which includes a variety of real-world images representing abstract concepts across 4 categories: strategic concepts, scientific phenomena, social relations, and domestic objectives. Each image is paired with questions that test understanding of the abstract concept, such as asking if there are clear entrances or exits in a maze. Our findings indicate that existing VLMs have significant room for improvement on this dataset. We evaluate DSG on VAD and demonstrate that it consistently enhances the performance of vision language models across different question types and abstract categories. Notably, DSG improves GPT-4V's performance by 5.4 percentage points overall and shows a 6.7 percentage point improvement in questions involving counting. While the challenge of understanding visual abstractions is not fully resolved, our results suggest that DSG is a promising approach that effectively structures the reasoning process for visual reasoning systems. In summary, we present Deep Schema Grounding, DSG, as a framework for extracting and grounding schemas of concepts, introduce the Visual Abstractions Dataset, VAD, as a benchmark for evaluating VLMs, and demonstrate DSG's improvements over previous models across various metrics. Section Summary. In this section, we introduce Deep Schema Grounding, DSG, a framework designed to enhance vision language models' understanding of abstract concepts by utilizing schemas that represent the relationships between visual elements. We also present the Visual Abstractions Dataset, VAD, a benchmark for evaluating these models' capabilities in interpreting diverse real-world images associated with abstract concepts, demonstrating that DSG significantly improves performance across various question types and models. Section: Related Works. In this section, we discuss related works in vision language grounding and reasoning benchmarks. Traditionally, visual language benchmarks have focused on understanding content in images, like objects and their relationships. Recently, more studies have evaluated tasks that require common-sense reasoning, often through "what if" or "why" questions, or by creating comprehensive scene descriptions. Our paper, however, highlights the challenge of grounding and reasoning about abstract concepts, such as unusual representations of scientific terms or unique strategic game setups. We believe these abstract concepts should be linked to lower-level concepts like entities and patterns, presenting new challenges for vision language models. We draw inspiration for our schema-based concept representations from cognitive science and artificial intelligence theories, which view concepts as organized around theories. Learning a concept involves understanding its theory, and reasoning with it requires causal explanatory reasoning. While many studies have focused on symbolic features for simple, concrete concepts, we propose using our schema representation to ground abstract concepts in natural images. Our approach relates to recent advancements in chain-of-thought reasoning, hierarchical image classification, and visual reasoning through programs. Unlike these methods, which mainly address object and relational reasoning, we concentrate on grounding scene-level concepts. Our framework also aligns with previous efforts that use vision language models to generate text descriptions for classification tasks. However, we introduce the generation of hierarchical schemas with large language models to ground visual abstractions for reasoning. Our hierarchical schema representation is akin to hierarchical program representations used in text-only reasoning, but we apply it to understand concepts in natural images. Notably, our deep schema grounding (DSG) method infers schemas using a vision language model, allowing us to utilize all visual information in an image for interpreting abstractions. We focus on reasoning about visual abstractions through visual question answering (VQA), although our approach can extend to other visual interpretation tasks. A VQA instance consists of an image, a natural language question, and an answer, which can be multiple choice or open-ended. We assume each image has an associated abstract concept, like maze, defined by a set of rules rather than specific visual features. The question pertains to this abstract concept, which is revealed to the models. The task of understanding visual abstractions presents challenges for existing vision language models due to the infinite variations of concepts in the real world. However, we note that the composition patterns of lower-level concepts remain consistent across variations, leading us to propose DSG as a framework that uses schemas to interpret and reason about visual abstractions. The DSG framework consists of three main steps: extracting a schema of the concept, hierarchically grounding this schema to the visual input, and using the resolved schema as input for the base vision language model. We define the visual abstraction schema as a concise program that represents a concept through a directed acyclic graph, DAG. Each node in this schema corresponds to a subcomponent of the higher-level abstract concept. For instance, a maze can be broken down into its layout, wall construction, and entry-exit positioning. The dependencies among these components create a DAG, indicating the order of interpretation. Importantly, the definition of these concepts is universal, allowing machines to generalize better to new scenes. Section Summary. In this section, we discuss the challenges of grounding abstract visual concepts in vision language models, emphasizing the need for a schema-based approach that connects lower-level concepts to higher-level abstractions. We introduce our deep schema grounding framework, which utilizes hierarchical schemas to enhance visual question answering by interpreting and reasoning about these abstract concepts through a structured representation. Section: Extracting schemas of abstract concepts. In this section, we explore how we can extract schemas of abstract concepts using large language models, LLMs, as a knowledge base. We believe that since LLMs are trained on vast amounts of human language data, they likely contain schemas that align with human understanding for various abstract concepts. Unlike previous approaches that translate natural language into programs, we focus on extracting structured knowledge based on the name of the concept. Our aim is to derive a universal schema that applies to different visual stimuli, rather than being tied to specific instances. We use a straightforward prompt for the LLMs, providing just one example schema for the concept, academia, which includes key elements like faculty and students, along with a brief instruction for generating schemas. We observe that LLMs can effectively extrapolate across many concepts and produce accurate breakdowns of visual abstractions. We include details of our prompts and the generated schemas in the appendix. Next, we discuss how we hierarchically ground these schemas in images. Instead of directly answering questions based on the image in the question, we first link individual schema components to visual elements in the image. For instance, in a maze example, we identify the materials of the walls and the maze's layout. We formally ground each component in the concept's directed acyclic graph, DAG, resulting in concise text descriptions like wall, coffee beans. We utilize pre-trained visual language models, VLMs, to predict the most likely grounding for each component based on the image and a text query. Our hierarchical approach ensures that components dependent on others consider the grounding results of prerequisite components, leading to more coherent and accurate outcomes. This method is essential for abstract concepts with various instantiations. For example, when addressing the maze concept, we first clarify broader components like layout before tackling more specific ones like entry and exit. We provide examples of schemas and their grounding in images, with additional examples and potential issues in the appendix. Finally, we use the grounded components to enhance our question answering process. For instance, with the maze concept and its grounded components, layout as rectangular, walls as coffee beans, and entry-exit as coffee cups, we enrich the final question answering step by supplying the VLM with this component mapping and the entire grounding conversation history. We frame the grounding in a prompt like, imagine that the image represents a maze, with a rectangular layout, walls made of coffee beans, and entry and exit as coffee cups. Our grounding system significantly improves performance compared to baselines that only reference the abstract concept. Importantly, our DSG framework operates solely during inference, utilizing the strong generalization abilities of LLMs for schema proposals and VLMs for grounding and reasoning, thus enhancing our understanding of visual abstractions. We use programmatic schemas as an intermediate representation to connect explicit common sense knowledge in LLMs with the visual reasoning capabilities of VLMs. To evaluate models on visual abstraction reasoning, we introduce the Visual Abstractions Dataset, VAD, which includes 180 images and 3 questions per image, totaling 540 test examples. This dataset features 12 different abstract concepts across 4 categories, with each concept linked to 15 real-world image examples. The questions cover various types, including binary choice, counting, and open-ended questions. We selected 12 distinct visual abstractions as concepts, all of which can be grounded in different objects and their arrangements in images. We focus on concepts that are not tied to specific visual features but require higher-level relational patterns. These visual abstractions encompass a wide range of scenarios and linguistic queries, grouped into 4 main categories. The first category includes strategic concepts, which are games defined by rules and patterns, such as tic-tac-toe, maze, and treasure map. The second category features scientific concepts that cannot be visualized in the physical world, like solar system, atom, and cell. The third category consists of social concepts involving intentional actions and role deductions, such as helping, deceiving, and negotiating. Lastly, the fourth category includes domestic concepts related to everyday household tasks, like table setting for 2, guest bedrooms, and door decoration, which are recognized by humans but lack a simple definition for their configurations. Section Summary. In this section, we describe our approach, DSG, which utilizes large language models to extract universal schemas for abstract concepts and hierarchically ground these schemas to visual entities in images, enhancing visual question answering. We also introduce the Visual Abstractions Dataset, VAD, to evaluate our model's reasoning capabilities across various abstract concepts, emphasizing their relational and lifted patterns rather than distinct visual features. Section Images and question answers. In this section, we curate 15 images for each abstract concept sourced from the internet. We ensure that these images are real, natural, and taken from the physical world, resulting in a diverse collection in terms of subjects, environments, and domains. We also create 3 types of natural language questions for each abstract concept in the Visual Abstractions dataset, VOD. These questions explore different aspects of the images and include binary choice questions, counting questions, and open-ended questions. Specifically, we have 6 types of counting questions, 14 types of binary choice questions, and 16 types of open-ended questions. For example, a binary choice question might ask us to describe the seating arrangement in a table setting image as either across or adjacent. A counting question could inquire about the number of organelle types in a cell image, excluding the nucleus. An open-ended question might ask us to identify the main color of the map region closest to a starting point in a treasure map image. Our dataset includes a total of 540 such questions, with answers labeled by 5 human annotators, and we use the most common response as the final answer for accuracy. While VOD primarily focuses on multiple choice questions, we also offer a free response version. We provide examples of each question type along with corresponding images and answers in the appendix, and we release our dataset. In our results, we validate deep schema grounding by comparing it to baseline visual language models, VLMs, and integrated language models, LLMs, using APIs on the VOD. We compare our work with models like Viper GPT, VisProg, LLAVA, InstructBlip, and GPT-4v. We also analyze different components of the DSG framework and demonstrate that it is model agnostic, benefiting both closed source and open source models. Baseline models receive the abstract concept in the prompt along with the question but lack DSG's resolved schema. All results are averaged over 5 runs, focusing on a systematic evaluation of multiple choice answers, where we calculate accuracy based on exact matches. Our findings show that VLMs benefit from breaking down abstract concepts into simpler components. We summarize the multiple choice accuracy of DSG with GPT-4v as the base VLM, showing that DSG significantly outperforms both VLMs and integrated LLMs across all question types. Notably, our method achieves an overall accuracy improvement of 5.4 percentage points, which is an 8.3% relative increase compared to GPT-4v. For counting questions, we see the largest performance boost of 6.7 percentage points, or an 11.0% relative improvement. We believe this improvement stems from more accurate labeling of objects through DSG, which connects concepts like the entity who is helping to specific elements in the image. We also report the accuracy of a random human annotator to emphasize the challenges present in VOD. Our analysis reveals that DSG outperforms GPT-4v across 4 concept categories, with a notable accuracy increase of 7.7 percentage points for strategic concepts and 5.9 percentage points for scientific concepts. The appendix includes qualitative examples of where DSG succeeds and fails in grounding schemas. Overall, we conclude that DSG's decomposition-based framework enhances the performance of VLMs. Section Summary. In this section, we curate a diverse dataset of 15 real-world images for each abstract concept, accompanied by 540 natural language questions of various types, which are labeled by human annotators for accuracy. We validate our deep schema grounding, DSG, method against baseline models, demonstrating significant performance improvements, particularly in counting-based questions, and show that DSG enhances the accuracy of visual language models across different concept categories. Section. Explicit hierarchical grounding of schemas is better than implicit and sequential grounding. In this section, we demonstrate that explicitly grounding schemas is more effective than relying on implicit or sequential grounding. We conduct ablation studies on different modules in our DSG approach, as shown in the table. Specifically, we evaluate 3 variants. 1. A version of DSG that uses only the schema generated by the large language model, without explicitly grounding each symbol. 2. A version where DSG performs grounding in a sequential manner rather than hierarchically. And 3. A hierarchical version where, during the final question answering step, we provide only the grounding results of each schema component instead of the entire grounding history. With the first variant, we assess whether GPT-4V can effectively utilize the schema without a structured thinking process. The second variant allows us to explore if breaking down the visual abstraction into key elements is enough to enhance the understanding of abstract concepts, while also examining the importance of hierarchical dependencies in grounding lower-level concepts. Lastly, we analyze the third variant to see if having the complete grounding trace of DSG aids in the final question answering step. Our results indicate that all these design choices are beneficial. Using just the schema does not improve performance, while hierarchical grounding from concrete to abstract symbols, along with the full context, enhances performance across many concepts. We also find that DSG improves the performance of other open-source visual language models, VLMs. In our tables, we summarize the results of DSG using the open-source LLAVA as the base VLM, showing a consistent overall improvement of about 7%. However, unlike GPT-4V, both LLAVA and DSG perform poorly on counting questions, as the base VLM struggles with enumeration, regardless of its understanding of abstractions.